This video will discuss the basics of multidimensional integrals. So let's say I have this one-dimensional function here, f of x equals 6 sine 3x. If I wanted to know the area under the curve from 0 to pi over 3, from 0 to 60 degrees of this function, I could do this definite integral. So I first find the function whose derivative is this function, which is minus 2 cosine x 3x, minus 2 cosine 3x from our integral rules. I evaluate this at pi over 3, subtract the value at 0, and evaluate the result, and I find that the area under the curve of this function between this function and the x-axis from 0 to pi over 3 is 4. That area is positive if it's above the axis and negative if it's below it. Okay, so we want to extend this to the analogous multidimensional idea. So let's say we have f of xy, and that function is 7x cubed y squared. And I want to know from minus 1 to 1 and 0 to 3, what is the volume under this surface? So think here. We have a function in one dimension times dx gave us 2 dimensions. So a value times another value gave us an area. Now we have a value times another value times, dx dy here. So we have a value times dx times dy. That's going to give us 3 values multiplied together. That's going to give us a volume. So in this case, f of xy is a surface. That's going to have a value which is either going to be above or below the xy plane here. If it's above, it contributes positively. If it's below, it contributes negatively. So that's called volume under the surface. Then the idea extends in general beyond that to functions of more dimensions, but it's harder to visualize because it's in either 4, 5, 6, etc. dimensions. It's hard to think in that many dimensions. So the last one we can really visualize really well is the volume under the surface here. Beyond that, it gets much more complicated. Okay, so we want to know the volume under this surface. So we can do this particular integral here. Integral minus 1 to 1 dy, integral 0 to 3 dx, 7x cubed y squared. So I'm saying that the limits of x are 0 to 3, the limits of y are minus 1 to 1, which I can also express this way, integral minus 1 to 1, integral 0 to 3, 7x cubed y squared dx dy, taking the inner limits to go with the inner infinitesimal. So the limits of dx are on the inside, limits of dy are on the outside. Okay, so let's try to evaluate this integral. One way I could do this is by factoring this function into a function of x and a function of y, and then doing the individual integrals. So I could say, well, by the scalar multiple rule, I can factor out the 7. Then in terms of x, it's x cubed, and in terms of y, it's y squared. X cubed doesn't depend on y squared doesn't depend on x. So I can factor those out of their respective integrals. And I can say I have an integral from minus 1 to 1 dy of y squared, which I'll write y squared dy for convenience, times the integral of the x part, 0 to 3 x cubed dx. Then I would evaluate each of these individual integrals. So I'd have 7 times 1/3 y cubed evaluated from minus 1 to 1, and 1/4 x to the 4th evaluated from 0 to 3. So then I'd have that this equals 7 times 1/3 times 1/4 of 1 cubed is 1, minus 1 cubed is minus 1, 1 minus minus 1 is going to be 2. 3 to the 4th is 9 squared is 81. 0 to the 4th is 0, so that's 81. So this is going to equal something that ends up being somewhat complicated, but is going to give me, in the end, 189 over 2. So the volume under this surface from minus 1 to 1 in y and 0 to 3 in x is 189 halves of volume units under this surface. So that's one way to do a multidimensional integral. Another way would be the following, to not factor them out. Let's say I want the integral from 0 to pi in y and in x of sine x sine y dx dy. All right, so I'm going to do the x part first, I suppose. So what I'll have is still the integral from 0 to pi. So the integral of sine is going to be minus cosine. So I still have my sine y part because that's a constant with respect to x. I can factor that out. Then I have integral 0 to pi of sine x dx dy. So within there, I'm going to have integral 0 to pi sine y times sine of x gives me minus cosine x from 0 to pi dy, still on the outside. Then I have integral 0 to pi sine y. Cosine of pi is minus 1. Minus 1 is 1. Cosine of 0 is 1. Minus 1 is minus 1. dy, this becomes a positive 2. I can now factor that out, and I have 2 times the integral of 0 to pi of sine y dy, which is equal to the integral I just did for x. So this is going to be equal to 2. So this is going to be 2 times 2, and the final result will be 4. So that's multidimensional integrals. Unless you want to pull some kind of special trick, in general you are integrating each of the dimensions one by one until you get rid of them and you have your final function as a result. Usually the easiest way to do that is to find a way if you can factor the function into a function of each of the individual variables and integrate them one by one. That's the easiest. If you can't, there are still other ways to deal with it, but it gets more difficult. And of course, being multidimensional integrals and the fact that most integrals can't be integrated exactly, there are way more integrals that can't be integrated exactly in many dimensions. So multidimensional integrals get very complicated in terms of doing exactly, unless you have very simple functions like these. But the main point is to understand the concept that it's the volume under the surface in 2 dimensions, or hypervolume under the volume in 3 dimensions. It gets very confusing very quickly. But that's the basics of how we integrate functions of more than one variable in more than one dimension.